So in this video, we're going to talk about limits of infinity, limits that approach infinity or limits that go to infinity. Um, the only time a limit is going to go to infinity is with a one-sided limit. Now, when I say that, these four examples that I have here are all one-sided limits. These are not as obvious to be considered one-sided limits, but let me explain. If I'm talking about the limit as x goes to infinity, I can only approach infinity from one side because infinity is a concept. I can't reach it from both sides, so I can only approach infinity from the left. Same thing for this. The limit as x goes to negative infinity is a one-sided limit because I can only approach negative infinity from the right side. So my answers for these could technically be positive or negative infinity instead of being a does not exist answer. So let's take a look at this rational function here. The limit, or sorry, just f of x is x plus 1 over 2x. So a quick review, finding vertical and horizontal asymptotes. Well, the vertical asymptote is when the function is undefined and we're not getting 0 over 0. So in this case, if x equals 0, we have 1 over 0, which is going to give us a function that's going to have a vertical asymptote right at the y-axis. Because if I plug in, I get 1 over 0. Also, we're going to review horizontal asymptote, that's top heavy, bottom heavy, or equal. In this case, the degrees are the same. So the horizontal asymptote, I look at the leading coefficients, I get 1 over 2. So we have y equals half. So just a quick review of what this graph would look like. The y-intercept, well, there isn't one. The x-intercept would be at negative 1. And so this graph is going to kind of look like this, right? Only has that one x-intercept, so it's got to stay off of the x-axis everywhere else but that one point. And so we can actually start to answer some of these questions, like the limit as x goes to 0 from the left. Well, if I think about that, if I do direct substitution here, I'm going to get 1 up top. 0 plus 1 is 1 over 2 times 0 is 0, which tells me that it's going to go to positive or negative infinity. So this is where we kind of think about this. Well, if I'm going to 0 from the left side, I kind of break a rule here. 0 is neither positive nor negative. But if I'm approaching 0 from the left side, that would imply that this product, like if I think about plugging in a negative number, something to the left of 0, it's going to be negative. So it's almost as if this denominator is a negative 0, which implies that a positive over a negative is going to go to negative infinity. And you can see it verified by this picture right up here. All right. So then if I do the limit as x goes to 0 from the right, 1 over 2 times, if I plug in a positive value very close to 0, like 0.001, that's going to be very close to 0, but positive. So I'm going to call this a positive 0, which means that this goes to positive infinity. The limit as x goes to infinity and negative infinity, well, that's just based off the horizontal asymptote. So the answer for these are just a half. And so the limits of rational functions as x approaches a positive or negative infinity is based off the power of the numerator and the power of the denominator, and in line with that, the leading coefficients, right? So if we have top heavy, it could be plus or minus infinity, right? That graph could go up forever or down forever because the top is growing faster. If it's bottom heavy, that implies that the denominator is getting bigger faster, which means that this function is tending towards 0 or the x-axis. And then if it's equal degrees, then we look at the coefficients, and then we would just say it's the leading coefficient over the leading coefficient. LC there standing for leading coefficient. But if I look at this first example, negative 2x plus 3, if I look at the degrees, degree of 1 over degree of 2. So this is a bottom heavy. So this answer is just going to be 0. The top is growing slower, the bottom is growing faster. If I think about that as like the fraction 1 over x, in comparison, 1 over, as x gets bigger, 1 over 10, 1 over 100, 1 over 1,000, that fraction gets closer to 0. All right, so the next one, a little bit trickier. It's top heavy, degree of 3 over degree of 2. So we now need to think about what's going to happen if I plug in a really big number. Now I really only need to focus on this because this is what determines the end behavior. Well, if I simplify that, that simplifies into negative 2/3 x, right? If I divide the powers of those using properties of exponents. Well, if I think about negative 2/3 x, that graph is going to have end behavior that looks like that. So as x goes to infinity, this graph is going down on the right side. Right? When I go this way, it's going down. And then therefore on the other direction, when I go to the left, to negative infinity, it's going up to positive infinity, right? When I go to the left towards negative infinity, the y values are going up, positive infinity. All right, last one here, number 3. We have equal degrees. So I have negative 2x squared plus 3x squared plus 1. I really only need to focus on those because that kind of determines what's happening for the end behavior. And I could just, again, do properties of exponents and see that that comes out to be negative 2/3. And so if the power of the numerator is equal to the power of the denominator, the limit is going to equal the leading coefficient or the leading coefficient. All right, so that's just filling in the information from before. Okay. So on this page, we have a whole bunch of rational functions. Again, you can look at the degrees. Some of them not as obvious, so I'm going to go over a few of those. So let's start with number 4 here. We have 4 minus 3 over x squared. And this is technically not a rational function, because, or it is a rational function, but it's not one single fraction. I could convert it into that, or I could just kind of use some number sense. Again, try to turn on your number sense here. If I think about the limit of 4 minus 3 over x squared, if I plug in a really big number for x, this fraction here, 3 over 10, 3 over 10 squared is 100, 3 over 100 squared, well, that's 10,000. So this fraction is getting closer and closer to 0. So we have 4 minus a value that's approximating towards 0. So we just get 4. Same concept here. We have x plus 1 over x. Well, I have infinity. Essentially, if I plug in infinity here, that number is going growing without bound, and this is going towards 0. So if you remember your schoolhood child days where you would say, I'm cooler than you, infinity plus 1, then you're just as cool as the person that says they're as cool as infinity. So infinity plus 0 is still infinity. All right, so I'm going to look at this next one here. That is essentially going to be a rational function that has e in it. So it's not actually a rational function anymore. I'm going to look at this by separating it and say, well, this is really the same as if I distribute the division, well, x over x, that's the limit as x goes to infinity of 1 plus, well, now if I distribute the division here, we have e to the negative x over x, which essentially you could say is the same as with the negative exponent 1 over e to the x times x. All right, so if I think about this, if I plug in a ridiculously large number, the 1 is just 1. If I plug in a really big number, 1 over e to the infinity, the denominator here is getting massively large really fast. So that's really like 1 plus 0. So that one again tends towards 0. Which means the answer to this is going to be 1 plus 0, so 1. Okay, so the last one I want to take a look at here is number 11. It's kind of an interesting case here. If we look at it, right, by direct substitution, let's just think about plugging in a big number. Or let's just start small. Let's say we plug in 10. So I get 10 minus, if I plug in 10 here, we get the square root of 102. So I get 10 minus the square root of 102. So that's a negative number, pretty close to 0. If I plug in 100, you're going to get 100 minus the square root of 10,002, which again is pretty close to 0. So we want to prove that this is going to be 0 because essentially by direct substitution we get infinity minus infinity. So this one's not so obvious. We're going to rewrite it as a fraction and multiply by the conjugate. So if I multiply the top and bottom of this fraction by the conjugate, what's interesting is that up top we have x times x, which is x squared, and the outers and inners cancel. When I multiply those, we get negative parentheses. The radicals go away, but the radicands stay. And in the bottom, we have 1 times the conjugate. So we have x plus radical x squared plus 2. That's the limit as x goes to infinity here. And so what happens is that this cancels with this, so we get the limit. If I distribute that negative, and we have negative 2 up top, right, when I distribute. And negative 2 over the bottom is now infinity plus infinity. So again, going back to our schoolhood days of when we're fighting in the schoolyard saying, I'm cooler than you, infinity plus infinity. Well, guess what? That's still infinity. And so the bottom is growing without bound, and this limit is going towards 0. All right, that should be it for the first part of limits of infinity.